Hello, in today's lecture, we are going to continue the discussions of weak coupling. And yesterday we did the same case. And today also we are going to do the same case with slightly different solutions. Yesterday we took the first case to be in the in the first case that we took was having some, we gave some kind of initial displacement to the left mass. Today we are going to give the displacement to the right mass. So let us start with the discussion. And the discussion would it's almost similar to the one that we did yesterday, and that is what I'm going to do today also. Okay, so the problem is has been, I think, that quite formulated yesterday itself. Again, I'm formulating it all over again. So here it was. We had a mass here, and this particular mass was given to be m, and these two masses were coupled using a spring of a differing spring constant. So we had a different spring constant given by kappa here, and here we had the spring constant small k, and here also we had a spring constant small k. Okay, and we wanted to find how the displacement would evolve as a function of time for both of these masses. And eventually, yesterday also we saw that there is some there would be some phenomena like beats. Okay, so let us do that. I mean, let us start with this. Okay. Okay. So give me a minute. Okay. So let us start with that. Okay. So as you're aware that let us first write the problem statement. And the problem statement is that we are discussing. It's just okay. Okay. So we are discussing what? We are discussing the case of the weak coupling. Case of weak coupling. Yeah, we can say weakly coupled oscillators today. Okay, so we are discussing the case of weakly coupled oscillators today, and with the initial conditions that your left mass is now at rest at t equal to 0. That is, I'll write at x, it is at rest, and it is not displaced also. And your right mass is now displaced to a point A at t equal to 0. So these are the initial conditions that are supplied to us. These are the initial conditions that are supplied to us. Okay. Now let us first write the equations of motion. So the equations of motion for both of these, like for left mass and right mass, would be okay. So for the left mass, this is not the initial position. Like it will remain at its own position. So at time t equal to 0, it has already been given that this is at A at slight displacement. Okay, it is at A at slight displacement. And now let us take it further. Like let's say this is your A, and we are just displacing it to right direction, x2. And also we are displacing sorry, t equal to 0 है ना, तो एक काम करते हैं t equal to 0 वाला केस लिखते हैं slightly पहले से ये. This is your initial time, and let's say at time t equal to some just after 0, plus you can say just del. What we are doing, we are trying to displace it slightly, this one with x1, and this one will go towards A plus x1, A plus x2. Already A is a displacement. Now x2, if you further move, it will be A plus x2. So net displacement in this, like net compression, this particular spring will remain x2 only. Don't worry about it. So now let us say this gets displaced by a distance x2. Sorry. Okay. So this is how it is. So now let us start. Okay. Now you see, whenever you have these coupled oscillators, and if the spring is extended, if the spring is extended, it will feel this way. It will try to come towards each other by the Newton's first law or Newton's third law. And if we compress the spring, so it will feel the force in opposite direction in accordance to the Newton's third law. Okay. Now understand, if we have to discuss this problem, we have to take some displacement criteria. So let's say x2 is greater than x1. Let us say x2 is greater than x1. So if x2 is greater than x1, what will happen? Since this is getting extended by x1, so your left mass, dynamics of left mass can be written in terms of your differential equation. And this x1 dot and x1 double dot is in the increasing direction of x. So this is the increasing direction of x. So I'm taking this as an increasing direction of x. So along this, we are saying that our x is increasing. Okay. So in this way, what I can do is mx1 double dot, I should write it as minus kx1 because of the first spring, you can see that it has been extended by a net displacement x1. And you can see that this particular spring will also get elongated. I mean, this particular spring will get elongated. So what will happen? See, I told you now, whenever your spring gets elongated, so what is the response of this masses? Like this is how the response would be. So this will be plus kappa. And how much is the elongation in the middle spring? The middle spring elongation would be x2 minus x, because A was already executed. So now, are you getting my point? So net elongation in the middle spring would be kappa x2 minus x1. And if I write mx2 double dot, it will be minus k. I should write kx2 because see, it is getting compressed by a by a quantity x2. So it will push it in this direction. And again, there will be kappa x2 minus x, and you can see here. So are you getting my point? So this remains to be the, this will be the your, what I can say. This is your differential equation governing the motion of x, governing the motion of the left mass and the right mass. Okay, so let us write that in little bit detail. Okay, so what it will be like, and I'll be giving it some signs, so that is something that we'll do later on. So x1 double dot would be equals to minus k upon m. I should write minus 2k upon m x1 plus k upon m x2, and then I should write x2 double dot is equal to minus 2k upon m x2, and then plus k upon m x1. This is how I'm going to write. Is that clear? Till now, I think it is clear. And
Yes, sir, you've taken K to be same for both springs, right?
no. I should write it in better manner. Symbol same name. See, this is small k, this is small k, and this is kappa, because we'll have to use the coupling condition. Huh? So you're right. I should write it as my mistake. ये जल्दीबाजी नहीं करनी चाहिए और चलो कोई बात नहीं हो गई जो गई. So this will be like let us do one thing. Let us try to decouple this differential equation. Let us try to decouple this differential equation by the first method that I taught you. What was the first method? The first method was to write some linear combination so that somehow our life becomes easy. So let us add these two equations. So if I add these two equations, I'll get x1 double dot, x2 double dot is equals to minus k x1 plus x2. And I will write small k again. Okay, so you can see that these are the normal coordinates. So x1 plus x2 is one such normal coordinate which is executing oscillation with an angular frequency root over k by m. Okay, so these are called as your normal coordinate. These are your independent coordinates which are executing your oscillation with one single frequency. So if you write this equation as x1 double dot plus x2 double dot plus k upon m, and you should write it as x1 plus x2 equal to 0, you can clearly figure out that this is your differential equation corresponding to a simple harmonic oscillator with the frequency root over k by m. So your x1 plus x2 as such, if you take x1 plus x2 as some different coordinate, let's say z, you'll find that this is z double dot plus k by m z. So basically what is happening, your x1 is individually functions of both k and kappa. If you solve this x1, you will find that your x1 would eventually come as a function of k, but it will contain both k and kappa. But x1 plus x2 will only contain this, like it will have only one single frequency. So it will be governed by one single frequency, that is root over k band. These coordinates are called as your normal coordinates, and the corresponding frequency is your normal frequency, and corresponding mode is called as the normal mode that we are going to see, that we've seen already. And let us divide it. So if x1 minus x2 double dot, if I want to find, it will come out as I think it will come out as, let us solve it. So it will come out as k x2 minus x1 plus kappa x2 minus x1, and I should write 2 here. Okay, is that clear? So overall, I know that my x1 minus x2 coordinate is oscillating with a frequency which is k plus 2 kappa upon, I should write m here. I should write m. I should not write m here. I'll write m here. And this will be x2 minus x1. And if I take this entire thing there on the left hand side, so I'll get a, like I'll write this as 1. And I will write this as 2. So this is my x1 double dot minus x2 double dot. And this is plus k plus 2 kappa upon m. And then I have x1 minus x2. So one of the frequencies of one of the normal coordinates is x1 plus x2. The other normal coordinates is x1 minus x2. Is that clear? And now let us place these initial conditions in order to get some solutions out of it. So my initial conditions were that my x1, let us, okay, so we can say that your x1 minus, sorry, x1 plus x2 corresponds to a cos omega t plus phi. So your x1 plus x2 is equals to a cos omega t plus phi, isn't it? So this is quite clear, because see, here you have this k by m. If I will write omega square is equal to some k by m. Okay. 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 So this is one thing. And another, x1 minus x2 will be equals to what? It will be equals to some, you take b cos of, and yesterday I took a symbol omega tilde, so I'll take again omega tilde here. This is k plus 2 kappa upon m plus square. Okay, so this is what it is. Okay, so if I use that, so I'll get omega tilde and then plus phi tilde. Now, if I use initial condition, if I use my initial condition, that is x1 at 0 was 0 and x2 at a was, x2 at 0 was a, I will get a is equal to a cos omega t plus phi. And if I differentiate both of them, so if I differentiate both of them and place x, so x dash plus x2 dash is equal to minus omega a, and I'll get sine omega t plus phi. And if I replace t equal to 0, what I will get? I will get 0 is equal to minus omega a sine phi. And from here, phi I'll get as 0. And similarly, if I have to find what will be phi tilde, so phi tilde will also come out as 0. And if you're if phi is 0, if phi is 0 at t equal to 0, cos will be 1. So capital A would be equals to small a. So capital A would be small a. What would be capital B? So if you want to find capital B, so I know that x1 minus x2 is equal to capital B. Okay. Phi tilde is already 0. At t equal to 0, x1 minus x2. So x2 is already, I think, a. So your B would also come out as a. If I'm not wrong, let me see. इसको ढंग से देख ही लेते ना. जल्दीबाजी क्यों कर रहे? So let us solve this. So your 0 is equal to minus omega tilde b cos omega tilde plus phi tilde at t equal to 0. So that will give you, sorry, this will be sine. So this will give you phi tilde to be equal to 0. This you've got. And second thing is at t equal to 0, this particular equation at t equal to 0, 0 minus a, because at t equal to 0, your x1 was at 0, your x2 was at a, and this will be b cos 0 because omega tilde is already 0 and 0 is 0. So that way you'll get b is equal to minus of a. I hope it is clear till now. I don't think there is an issue till now. In fact, instead of using this omega tilde and all those things, what we can do, we know that your omega tilde, okay, your omega tilde is given by k upon m plus 2 kappa upon m put over. So I can say that this is your um, faster frequency. So at times you'll find in book this kind of notation also written omega f, and omega at times, you know, this is your slower frequency. So I'll write it as omega s. Will that do? Or should I use this omega tilde omega omega? Like whatever suits you, you can do that also. Is that clear till now? इसमें कोई दिक्कत तो नहीं है अभी तक?
Yes, sir, clear.
Okay. So this is to just denote omega f is to just note that this is your this is having greater frequency, like this will be oscillating with a greater angular frequency than this. So faster and slower, nothing else. So if I use these notations and if I just try to construct my solution back, so what I'll get, I know that my x1 was x1 plus x2 was what? So your x1 plus x2 is what? It is equals to a. And if I write cos, sorry, if I write cos, and then I should write omega t. I know that my phi is 0, so I'll not use that. And my x1 minus x2 is nothing, but it is equal to minus a. And I have cos omega again tilde t. I hope it is clear or not clear. कुछ गलती कर रहे हैं क्या? Are we doing some mistake or what?
No, sir, it's correct.
It's correct. Huh? So in any case, this is what we are right now getting. Okay. Or you can say omega s and omega that thing. Like if you want to use omega s, एक ही symbol use कर लेते हैं यार. x1 is equal to a cos omega s, and x1 minus x2 you will get a cos omega fast t, and then you'll have minus. Okay, and so if you add them up, you'll get x1 as a function of time, and that would be, I think, 1 over 2. So I'll write a upon 2, and I'll write cos omega st minus cos omega ft. And I told you yesterday that we use certain symbols that I'll use later on. So x2 will be a by 2, and this will be like cos omega st plus cos omega ft. I think this is quite clear. So x2 as a function of t, you know, x1 as a function of t, you know. And I told you yesterday that for certain reasons that you'll come to know again later on, omega s can be written as omega s plus omega f upon 2 minus, you can write it as omega f minus omega s upon 2. This was 1. And omega f again you can write omega s plus omega f upon 2 plus, again you can write omega f minus omega s. Is that clear? But these are you can take in this fashion. So omega s plus omega f upon 2, and you can write omega f minus omega s upon 2 and omega f. So I think this is quite clear, and you can take this particular entire thing as some another symbol, and you can use this particular symbol as epsilon as used yesterday. Is that clear? Okay.
Yes, sir. Sir, in our solution, what does phi represent, sir? Initially, which we
Phi,
took.
okay. देखो यहाँ पर phi would represent your initial phase of the motion. Initial phase of the motion means, let's say here it is a spring now. Here it is spring, so we have taken phi equal to 0 only. But let's say if it was a spring, it was a pendulum. Let's say if it was a pendulum, and we had coupled it with some something on that sort. So if this is the case, if you're disturbing your pendulum from here, so initial phi is 0. Like there is no such angular displacement given to it. Now, if you displace it from here, yeah, some initial displacement is given. Let's say pi upon 6. So this particular phi in general is called as your epoch of the motion, your initial phase of the motion. So from where you are initiating your motion, that is how it is. Or what should I say right now?
Just, It means that phi and phi tilde are different.
Phi and phi tilde are different. But in general, I've taken them different. And however, uh, from the initial conditions, I've come to know that both of them are zero. Right now, I'm not able to explain you quite physically what it would mean, but in general, in theory of oscillations, what we take this phi, let's say for oscillators, let's say for uh, you can say for your simple pendulum, if you from where you initiate your motion, like what is the initial phase to initiate the motion? Let us say your pendulum is here, so your phi would be zero, but or you just initiate a motion from here, like phi is equal to some angle, let's say pi by 6. So your initial phase of motion is pi by 6. And if you initiate from here, it will be some angle. So what is at t equal to 0? What is your phase? Well, from where you are initiating the motion? From what angular displacement you are initiating the motion? This is how you know phi as in general. However, here I have taken to make it a more sort of generalized thing. Even if you would have not taken this, five things would have remained the same. This is what is getting inferred from here. Because there is as such, I don't believe there is as such some angular displacement here. So basically it is all along line. Uh, this is what I understand right now. Like physically, I'm not able to explain, but this is what it is. Okay. Okay. So this is what I feel till now. So like these symbols are quite difficult, but somehow you have to see it. So why do I take epsilon? That you come and see later on. And you see that overall, if I use one formula that we studied in standard 12th, that is cos C minus cos D, that is equal to A. This is equal to 2. So this will come out as sine omega S plus omega F upon 2t, and then sine omega F and SA x2 as a function of t, you will get A, and you will get cos omega F plus omega S upon 2t, and then cos omega S minus omega F upon t, and this is like t. Is that clear? So your x1 as a function of time, you're getting as A, I think sine, and omega S plus omega F upon 2, that will be like simple this, and sine, then I should write epsilon t. And similarly, x2 as a function of t, you will get A cos this, and then cos epsilon t. I hope it is quite clear. Now, if omega f is quite close to omega s, that is in the case of weak coupling. In the case of weak coupling, this will happen because in the case of weak coupling, your kappa is very, very, very less than small k. So your omega f that I'm stating, that is equals to omega plus, or you can say omega s plus 2 kappa upon m will be equivalent to saying that your omega f is almost equivalent to omega s, or like there is this increment is not that significant. So that increment I've already stated as epsilon. Is that clear? So omega f
Yes.
minus omega s is 2 kappa, and if it is a very weak coupling, I'll say that this is quite very, it is very quite small. So this is how it is. Okay, are you getting my point? But for the case of weak coupling, I can
Yes, sir.
say that my omega f is quite close to omega s, or you can say for weak coupling, for weak coupling, your epsilon would be very, very less than this. I'm writing it for the case of the weak coupling. And this we did yesterday also. No? I expanded this term, like if you remember, I expanded this term also. So I wrote this kind of thing that omega f is equal to, I think I wrote it as square with the k upon m, and then I wrote it as 2 kappa upon m, and then I wrote rho 1 over 2, and then I took a binomial expansion to it, provided that your kappa is very, very less than k. So what will happen? You take root over k by m common out. So I took root over k by m common out, and this was 1 plus kappa upon k. Okay, and you know that this is very, very small because kappa is very, very smaller than k. So you can expect that your omega f is almost equivalent to omega s. However, it is slightly greater, but it's not that great. So this is the case of weak coupling, or in other words, you can say that omega f minus omega s would not be a significantly large term. So it will be very small. So let us compare these two terms. And if I say that epsilon is very, very less than like omega, it implies that I'm talking of some of weak coupling. I'm talking of weak coupling. So we are talking of two oscillators which are weakly coupled by a spring whose spring constant is kappa. Okay, so this is how it is. And okay, so this is decoupling. So if I just think about, so these are the solutions. I mean, this is what you have to till this is the portion till which you have to solve in the exam. Okay, now particularly in exam also, if somebody asks you thoda sa zyada isse, what they can ask, they can say that how would the graph would be, or probably uh, how would the graph would be, nothing more than that. Okay, so you can see that if epsilon is very, very less than this, that is omega, what will happen? That's this term. I can say that uh, in the term x, like the left mass will oscillate dominantly with angular frequency omega, and oscillations governed by the latter term. Oscillations governed by latter term, that is sine epsilon t and cos epsilon t, is much slower. And I tried to draw an analogy for this. I told you that, let's say here's the graph. If I want to make a graph of sine x, how it would look like? It would look like this way. Okay, this is how your sine x is. If I want to make sine pi by 2, what will happen? Sine pi by 2 will rise, and at pi by 4 it will attain some maximum. At pi by 2 again it will attain 0. At 3 pi by 4 again it will attain -1. At pi it will again attain 0. And this is what it is. So now it is starting to gain rapidly. And if I take sine 4x, so it will make more rapid oscillations. Is that clear to you? And if I increase the frequency, or if I increase the multiple term with x, I can see that my frequency of oscillation would increase. As frequency increases, now my sine would wiggle more, or you can say that the sine graph will oscillate more, or you can say it will oscillate more from to and fro. Is that clear or not? मतलब समझ पा रहे हो मेरी बात? So sine इसकी तुलना में, compared to this will oscillate uh, much faster than sine epsilon t. Is that clear? And similarly, I can say that cos omega t will oscillate much faster than cos epsilon t. Is that clear? So more or less, in the time interval of oscillations for this will remain almost a constant. Okay, or you can say that this will act as if it is an envelope. So these two things will act as an envelope. So if you see also, generally कैसा होता है? A sin theta होता है ना? Now you are having A sin epsilon t, and then you have what you can say, and then you have sin omega t. So देखो, in the time that it is oscillating rapidly, your sine is slowly decreasing. Like sine epsilon t is slowly decreasing. So basically, you have an amplitude which is again governed by a function of time. So sine omega t's amplitude is again governed by a function of time, which is oscillating, or which is changing at a lesser rate than how it is changing. Like this is rapidly changing to and fro from -1 to +1. Is that clear? So it will act as if it is an envelope. It will act as if it is an envelope. Is that clear or not clear?
Yes, sir.
Okay, so it will act as if it is an envelope. Okay. Now, so what will happen? So what will happen is I will try to make the plot of it. So let us first make the x1 as a function of time. So x1 as a function of time, we know that it is sine omega assign epsilon t sine omega t then. So I'll make the graph of sine epsilon t. So like sine omega t, and the amplitude is this. So I can write this as a function of time. So this as a function of time will be enveloped between minus sine epsilon t to plus a sine epsilon t, because sine theta mostly varies from -1 to 1. It varies from -1 to 1 for all times. So obviously this particular function would be enveloped between sine epsilon t, and this will be minus a sine epsilon t by t. Okay, is that clear? Now, if you see in this, what is who is executing oscillations rapidly? This is executing oscillations. So I'll make the graph of it. So what it has to be enveloped between this only. So this is how your sine omega t would look like. So this is what I taught you yesterday only. So this is what I was selling also, that nothing would change if you replace initial conditions of x2 instead of x1. Only the functional form has changed, but uh, overall the motion would look like this. Is that clear to you? So this is like, what should I write? So this is your a sine epsilon t, and this is your a. Sorry, this is your sine. Is that clear? And secondly, with the other one would start with cos. So I'll write it as it will start from 1, and when it will be pi by 2. हल्का से आइडिया ले लेते हैं, यहाँ पे कहीं पे pi by 2 आएगा. So then again at this particular point, so it will again attempt to be a minus. Then again it will be like, and the same is the case for this. Like, okay, is that clear? Okay, till now. Okay, so here your cos will oscillate oscillation. So cosine will start from here. This is what it is. Okay, is that clear? So this is your cos omega t, and this is your a cos epsilon t. Is that clear? Now, so you can see this is the graph for the where your displacement as a function of time is plotted for the left mass, and this is the graph where displacement as a function of time is written for the right mass. Is that clear? So you can see that at t equals to some pi by 2. So here it is like t equals to pi here. At t equals to pi by 2, you can see that the second mass is getting 0. Like the displacement is getting towards 0. So I'll write it here. So this will be like t equals to pi by 2, and I should write epsilon here also, because cos becomes 0 when your epsilon t becomes pi by 2. Okay, so at this time the second mass will not be moving, but you can see that at this particular time your first mass is at the maximum distance from from t equal to 0, that is from the equilibrium position. Is that clear?
Yes, sir.
Okay, is that clear? So at the start, you can see at the very start, that is at t equal to 0, that only your second mass was moving. Your first mass was not moving. That is x1 was at x1 at t equal to 0 was 0. But x2 at t equal to 0, you can see all the motion is contained. So at t equal to 0, all the motion is contained with the right mass. And slowly you can see that at t equals to pi by 2, this particular what you can say that this particular second mass is not moving at all, but the first mass is having all the motion. It is at the maximum displacement. You can see. Is that clear? And then at further time t equals to pi by 2 epsilon, if you take, your second mass will contain all the motion. However, your first mass is coming to the rest. Is that clear?
Yes, sir.
Okay. So what you can see that, in other words, you can, in terms of oscillations, in terms of energy, we say that basically there is an exchange of energy between x1 and x2, and all the energy is contained with x2 when energy is not contained with x1, and all the energy when contained with x1, we will see that there is no as such energy contained with x2. Is that clear?
What, sir? Please repeat the last line.
Okay. So what I want to say, one thing that you should understand, that ऐसा समझो, मैं जो समझाने की कोशिश कर रहा हूँ, one thing that you should understand, and write it here so that समझ में आ जाए. One thing that you can see that x2 is always at 90 degrees phase difference with x1, or other way around, you can say, with x1.
Yes,
Is that
sir.
okay? So you can see that जैसे ऐसा समझो, जैसे कि जब x2
Yes,
के
sir.
पास सारा motion contain होगा, when x2 is having all the motion, your x1 is at rest, and when your x2 is coming to 0, that is, if your right mass is coming at time t equals to pi by 2 epsilon, your right mass is coming to rest, but your all the mass is contained with x1. All the motion is contained with x1. So you can see that energy is getting transferred between x1 and x2. So when it is coming to the least kinetic energy, it is getting to the maximum kinetic energy. Is that clear or not clear?
Clear, sir.
So this is a kind of pattern you may see. और इसी को मैं लिखना चाहूँ तो मैं इसे लिख भी देता हूँ. I am not very sure कि कितना I'll be technically right, but you can say that the right mass is always doing some positive work on the left mass, and left one is doing some negative work. इसको कैसे समझें? एक मिनट समझते हैं. Negative work. So what is happening? Since we've taken x2 to be greater than x1, so x2, if it is greater than x1, so this will like try to push it in this direction. Are you getting my point? So it is actually executing some positive work. So displacement is in this direction effectively, and you can say that the right mass is doing some positive work on it. However, as you can see that this particular mass wants to come here because of its compression. So you can say that this mass is doing negative work on this mass, because now the displacement is in this direction, it wants to come in this direction, and this is all happening because of the coupling of these two masses only. So, or other words, you can say that जब ये चीज यहाँ पर होगी at the maximum velocity, this will come at rest, and when it will be at a maximum क्या कह सकते हैं, what should I say, um, uh, like when it will contain all the motion contain करने का maximum velocity से होता है. So ठीक है, when it will contain all the maximum motion, it will come at rest. So basically kinetic energy is getting transferred between m1 and both of these masses. So there is a transfer of energy. Is that clear or not?
Yes, sir.
So this is like these are all physical implications, or you can say that possibly this is how mathematics is done. But हो सकता है कि बहुत physics oriented आदमी हो तो वो इसी चीज को अलग अलग तरीके से options में लिखेगा, and then things may become slightly difficult for you. I'm not able to explain it to you in the very right sense, but this is what is my intuition says, that such questions like this is everybody knows. This is some graph that everybody would see in any waves and oscillation book. And I would insist that any such, if you can find, there are many simulations to it given. So you can see simulations to coupled oscillators also on internet. Okay, so this is the end of the discussion as much as I understand about coupled oscillators, weakly coupled oscillators.
Sir, you have related this to phenomena of beats also, no, yesterday.
Yeah. Okay, so there is 1 minute. I'll talk on that in the next session. Will that do?
Yes.
Okay.